Hello, everyone. Thank you for inviting me to this very nice workshop. And today I'll be talking about designing photo-induced superconducting devices. Basically, I will introduce a very simple mechanism that leads to photo-induced superconductivity. I will also make the argument that such a mechanism can explain long-lived superconductivity in the context of K3C60. And then, since the mechanism is it's simple enough, I think we are in a place where we can really go ahead and engineer devices where we might be able to see photo-induced superconductivity in more and more platforms. Okay, so let me get right into it. We heard from all the speakers about the many functionalities we can get by pumping materials. Here I want to focus specifically on a very ambitious project, which is to take something that was not superconducting, and then when you pump it with light, it becomes superconducting, and then the holy grail would be not just to create it, but then to keep it for a long, long time. And this idea really started taking off with Andrea Cavalleri's group and Matteo doing this experiment on pumped K3C60, where they've seen signatures of superconductivity. They've seen those signatures persist up to 300 Kelvin. But very interestingly, they've seen that those signatures would live for 1 to 10 nanoseconds. I know there was a previous talk about human scales. Okay, this is pretty short-lived, but for the electrons and the phonons that live picoseconds and hundreds of femtoseconds, 1 to 10 nanoseconds is really infinity. And I'll try to capture this. So for the theorists, it begs the question, how do you photo-induce superconductivity? And when you induce it, can you keep it? And for this conference specifically, can you then use this knowledge to create new platforms where this can happen again? Okay, I'll mainly be presenting 2 papers that we recently put out on arXiv, one by Sambuddha from Harvard and the other one from Christian at the Max Planck in Hamburg. Okay, but let me first take a step back and ask, why is this such a hard problem? Can we trivially do this? And if we go back to conventional superconductivity theory, phonon-mediated, let's say BCS superconductivity, we have a single electron band. We couple this single electron band locally with a phonon. And then by integrating out the phonon, we find an electron-electron attraction mediated by this phonon. But crucially here, the interaction doesn't depend on the number of phonons I have in the system. Pumping more phonons in the system doesn't increase the attraction. And in fact, the only thing it does is heating up the system and ruining our superconducting state. And then, since we're talking about photo-induced, let's see how light coupled to matter. And light couples to matter typically through this vector potential times current interaction. And this leads to the usual Biot-Savart law, where current going in opposite direction repel, while going in the same direction attract. So actually for Cooper pairs, such a light-matter interaction is repulsive. It's bad for Cooper pairs. So we went ahead and did the, let's say, next simplest thing, if you like. We considered 2 bands that are separated by a band gap. And now we have a boson that is coupled to the interband transition rather than the density. Right, yes. Up. What's happening? Okay. Yes, 2 electron bands, 1 boson coupled to the interband transition. For the rest of the talk, I'll basically be presenting properties of this Hamiltonian and this model. And in particular, now we can consider this to either be a phonon or it can be light coupled to some dipole transition between 2 bands. Okay. In this model, we treated 2 cases separately. One case is when I take the boson and I statically shift it, let's say like a Raman mode. The other case is when I populate real phonon occupation. And interestingly, in perturbation theory, in both cases, you find, okay, first of all, you find a 4th order in the coupling attraction. So it's pretty small, which is why we usually don't think about them for equilibrium superconductivity. But even though it's small, it comes with a Q² prefactor, which means that if I pump it, I can now activate it. And I can now enhance my electron-electron attraction by pumping. So we have a handle of photo-inducing superconductivity. And in the driven phonon, when I populate real phonons, these oscillations give rise to further resonances when the gap between the 2 bands is resonant with the phonon oscillation. Okay. So first, let me start with the static distortion case. Turns out that this scenario presents a very realistic model for photo-induced K360. Let me tell you a little bit about K360. It's made out of this, let's say, C60 vacuoles. And close to the Fermi surface, the relevant degrees of freedom are these triply degenerate T1U bands. And in fact, in the theory, they have been treated as degenerate. But actually, once you put it in the crystal, at the gamma point, they're degenerate. But then they split, and you actually have a very big separate. They become very well separated into 2 half-occupied bands and 1 completely empty band, tracking very closely to our model. And the material itself has these Jahn-Teller modes, which are these distortions of the vacuole that are very, very strongly coupled to these 1 TU bands, providing all the ingredients for our model. The idea here is that at any frequency you pump, because the Raman mode couples to E² of the electric field, then you can statically distort this Raman mode through Raman rectification. So you distort this mode, this enhances attraction, and this can induce superconductivity at a higher temperature. So that's the idea. Let me show you a bit more about how well this tracks with our model. If you look at the density of states, this is in gray. In DFT, the density of states are in fact very peaky. And they're very well separated, making our assumption a very good one that these are really like bands that are separated by a band gap. And we matched the ab initio formulated model to our model, and let's say use this as the band gap and the correct density of states. This material turns out to be also close to a Mott insulator transition. So actually, Mott physics tend to renormalize both band gaps and density of states quite significantly. So the strategy we adopted here is to allow the gap and the density of states to be free parameters and see whether we see anything interesting within the numerically allowed space. And indeed, not only we found superconductivity, but we found that there are 2 ways that this superconductivity can be long-lived. This model already hosts a metastable a metastable point with a higher, of a better superconductor and a static Jahn-Teller shift distortion. In this scenario of metastable superconductivity, the gain captured from creating the superconductor from the condensation energy overcomes the elastic energy of the phonon mode. And here we have another scenario that I will go more in detail, where even in the absence of metastable superconductivity, where the phonon mode is not trapped and rolls back to equilibrium, if you open up a big enough superconducting gap in the electronic sector, that gap itself can act as a bottleneck for your thermalization. Meaning that now, in order to thermalize, you need to excite, you need to generate quasi-particles across this gap, and this, I will argue, can be a slow process even at high temperatures. Okay. So let me first walk you through the metastable superconductivity. There's two types of metastability. Either you always have a metastable minimum of a slightly better superconductor. So now above the transition temperature here, I can push with my laser the phonon coordinate. It gets over this hump and gets trapped. And in principle, it gets trapped for a long time. It's unclear what makes it decay. Probably grain boundaries would bring you back to the normal phase eventually. And then there's metastability too, where the coupling is so good between the superconductor and this phonon coordinate that actually the metastable point becomes the global minimum at low enough temperatures. And this is associated with a prediction of a first order phase transition in equilibrium. Turns out experiments cannot rule out this first order phase transition in K3C60, just because both the distortion is very hard to see, and also heat capacity data in disordered samples can smear out first order phase transitions. Here, this is the phase diagram in terms of how close these bands are to each other and how big the density of states is. And from DFT, we are in the normal phase, but as we renormalize the band structure down, we can easily end up in the real material, either in the metastable 1 or metastable 2. So at this point, this is definitely a plausible scenario where the ab initio parameters that we fitted in our problem place us right at the edge of whether an interesting thing can happen or not. So now let's discuss the second scenario. In this scenario, we are basically in this, in this normal region where there is no hump and there is nothing preventing for the Q to go back. The idea here is that I pump with my electric field this shift my Raman mode statically, which increases the attraction and opens up a superconducting gap. But then as soon as the pump goes, the phonon also disappears. And then the electron system is left with, which is with its equilibrium distribution. Sorry, with its equilibrium attraction. So the idea here is that as you open the gap, electrons scatter off and combine into Cooper pairs. So doing this procedure eventually effectively gets rid of quasi-particles here. And then you end up in a state with the original equilibrium attraction, but no quasi-particles. And this state will last for the time it takes to create pairs of quasi-particles. So first, let me discuss a little bit about the state. In order to find what this steady state is going to end up being, you solve the BCS problem at fixed temperature, because scattering within the band is going to be very fast. We calculated on the picosecond time scale, but generating quasi-particles is going to be very slow. So this is going to be described by a temperature, and then we solved our BCS gap equations for a particular temperature, but also fixing the number of quasi-particles, because we're saying changing quasi-particles can be a very slow process. Okay, and how do we calculate the time scale? We use Fermi's golden rule to estimate how long does it take for a phonon coordinate, for a phonon mode to come in and excite across the band to a pair of quasi-particles. Okay. It turns out K360 is particularly lucky because once you get rid of enough quasi-particles, the superconducting gap comes somewhere in here where there are very few phonon modes to equilibrate you. And this is not just in K360. In a lot of materials, you can have the superconducting gap being in a region where you don't have a lot of electron-phonon spectral weight, and that gives you Cooper pairs with very long lifetime. And this long lifetime also will translate in a long lifetime for your photo-induced superconductor. So kind of this is the main message in this section. If you want to find another long-lived superconductor, you better look at systems where in equilibrium they have very long Cooper pair lifetimes. And there we used from the literature A square F, and indeed we evolved our state and found 2 nanoseconds time scale at 100 Kelvin. Let me just point here that I start from this gap here, and as I generate quasi-particles, I melt my gap. And once I reach this omega maximum where I have a lot of electron-phonon spectral weight, I crash down in an avalanche way in 1 picosecond. And this would be, so what we predict for this experiment is that there is a distortion that's important to create the state, but also the time dynamics will be of this avalanche type. Okay, how long do I have? Very good. For the next 5 minutes, let me tell you how to use this theory to create this in the lab. Okay, so before I was talking how to take advantage of the static shift. Here, I'll try to argue that if we drive real phonons into the system, we can get further enhancement of this attraction coming from resonances between the band gap and the phonon frequency. This is from perturbation theory. So we did, just to check our sanity, we did exact diagonalization calculations on a 2-site model with 2 levels, 2 electronic levels. And on each side, I'm coupled to a phonon. And I looked at the probability of having the electrons together versus not. And in equilibrium, we don't see any resonance, and it's just the 4th order attraction that you get. But as soon as I pump a little bit, I see this massive increase in the probability that the electrons are going to be on top of each other. And in fact, on resonance, I get this massive resonance. And I want to point out that this is a logarithmic scale, so it's a pretty big effect. To look at extended systems, we used many-body field theory and integrated out the phonon and computed self-consistent equations for the band, for the superconducting gap in the upper band and the lower band. And after a lot of work and many Matsubara sums, we ended up with something that looks like a BCS gap equation. And the first term we get is the G to the 4th attraction. It's a usual BCS equilibrium term. But on top of that, we get a term that is resonant once the band gap is very close to the phonon frequency. However, this term is suppressed in equilibrium because it's proportional to the number of phonons you have. And in equilibrium, this number of phonons will be in the ground state, it will be 0. Okay, so we use some very simple band structure and saw that indeed, if you put one boson into the system, you get this massive increase in the estimate transition temperature close to the resonance. Crucially, the biggest enhancement we get is when you are ready tuned from the resonance. And this is very good because when you are ready tuned, you also don't allow any direct electron transitions. So obvious heating methods are turned off in this ready tuned region. Okay, so we went to a realistic material. The idea is, how do you make a device out of this? And the idea is to put 2D materials placed on surfaces. The 2D material will give you a band structure, will give you a pair of bands, and the surface will give you a surface plasmon that will give you a very flat band of bosonic degrees of freedom. So literally the first thing we thought about and wrote down was put graphene aligned with HBN on top of STO heterostructure. Around the valve cone, although we use the full band structure here, there is a gap that opens up because of the alignment with HBN. And this is coupled through the vector potential to the surface plasmon polaritons modes in STO. STO has very soft surface plasmon polaritons that match exactly this gap. And that way you can get very strong enhancement of this attraction. And okay, just to really put it as a concept here, we have STO, 5 nanometers of HBN, and graphene. And then the challenge is that we need to excite these surface plasmons. So one of the ideas, of course, I welcome any other ideas you guys have, is to put an STM chip, STM tip, and excite surface plasmons at 5 nanometers away from the surface again. And we estimate here, if we excite one boson per momentum mode, we get something like a TC of 15 Kelvin for graphene, which we also took into account repulsion in graphene. And the energy that we put into the system amounts to heating of 1 Kelvin. So it's a question of whether this will happen. And this is literally the first thing we tried. The idea is that this is just the beginning. In principle, we can find a more like idealized 2D material and surface to push this photo-induced state to higher and higher temperatures. Okay, and this is the summary. Thank you. Okay, I want to thank my collaborators, the gifted PhD students that worked on this, Sambuda from Harvard and Christian from Max Planck, and all the senior people, Eugene, Michael, Angel, Dante, and Andrea Cavalieri. Thank you.